Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this green shape that is inside square ABCD. And in the second question, we'll find out the area of this green shape that is inside quarter circle AOB. So we start with the first question. In the drawing, we have square ABCD. We know that this is angle PQC, that is a right angle. This is line segment PQ, that is equal to 2 units in its length. This is line segment QC, that is equal to 3 units in its length. And our mission is to find out the area of this green shape. So first of all, we know that all the angles inside the square are right angles. So those 4 angles, they're all right angles. So this is a right angle, this is a right angle, this is a right angle, and finally this is also a right angle. In addition, we know that all the sides of a square are equal to each other. That is to say, AD equals to DC equals to CB equals to BA. So we will define one side of this square ABCD as A, and therefore all the other sides must be also equal to A. So this is side AD. That is equal to A units in its length. This is side AB. It is also equal to A units in its length. This is side BC, equal to A, and side DC also equal to A units in its length. We define this line segment QB as X. So what is the length of line segment AQ? AQ equals to AB minus QB. AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X units in its length. In the next step, we'll define this angle, the direction angle QCB as alpha. So in the right angle QBC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. We know that AB is one side of square ABCD, therefore it is absolutely a straight line. So if you focus on this side, the right side of the straight line AB at point Q here, so here the sum of the angles must be equal to 180 degrees. According to rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is equal to 90 degrees minus alpha. This is a right angle plus this missing angle. In total, the sum of those 3 angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q. Exactly according to rule 3. In the right angle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy this right angle APQ and this right triangle QBC. Then you page and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that they call it from the original drawing. This is the right triangle APQ, this is the right triangle QBC. So in the next step, we'll prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So actually this is angle AQP. In the right triangle APQ, and it is equal to this angle, that is actually angle QCB. In the right triangle QBC, they are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually this is angle QAP. In the right triangle APQ, and it is equal to this angle, that is actually angle QBC. In the right triangle QBC, they are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle APQ. In the right triangle APQ, and it is equal to this angle, that is actually angle BQC. In the right triangle QBC, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles in this right triangle APQ are correspondingly equal to all the three angles of this right triangle QBC, and therefore those two right triangles can go into each other according to angle similarity rule. So I write it down. Triangle APQ, this triangle APQ is similar. This is the sign of similar to this right triangle QBC So angle, similarity rule. And for the fact that those two right angles are similar to each other, we derived that the following relationship exists between their sides. We will derive that side AP of the right angle APQ over side QB of the right angle QBC is equal to side AQ of the right angle APQ over side BC of the right angle QBC, and it is also equal to side PQ of the right angle APQ over side QC of the right angle QBC. So I put again. We derive the side AP of the right angle APQ over side QB of the right angle QBC equals to side AQ of the right angle APQ over side BC of the right angle QBC, and it is also equal to side PQ of the right angle APQ over side QC of the right angle QBC. AP is the missing side, so we leave it as it is, over QB. QB equals to X, and according to equation 1, it is equal to AQ. AQ is A minus X over BC. BC is A, and it is also equal to PQ, that is 2, over QC, that is 3. So total, according to equation 1, we actually found out that AP over X equals to A minus X over A, and it is equal also to 2/3. Actually, those two expressions are equal to each other, so we create equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that AP over X equals to 2/3. Here we multiply this equation 1 by X, and finally we get that according to equation 1, AP equals to 2/3 X. So according to equation 1, AP equals to 2/3 X. Those two expressions are also equal to each other, so we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that A minus X over A equals to 2/3. So we will of course multiply this equation 2, and we find out that according to equation 2, 3 times A minus X equals to 2A. We open the brackets on this side of equation 2, and we get that 3A minus 3X equals to 2A. Here we subtract 2A from this equation 2, and finally get that according to this equation 2, 3A minus 2A is A, so A minus 3x equals to 0. Here we let 3x to this equation, equation 2, and finally get that according to this equation, equation 2, a equals to 3x. Okay, then, repeat again, we found out that according to equation 2, a equals to 3x. In the next step, I'll copy this right triangle QBC in the new page, and we will implement the Pythagoras theorem in this right triangle, triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle QBC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. So write it down. This will be equation 3. QC squared equals to QB squared plus BC squared. So repeat again, according to equation 3, QC squared equals to QB squared plus BC squared. The hypotenuse QC is 3, therefore QC squared is 3 squared, that is 9. And it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, according to equation 3, we found out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we have only found out that a equals to 3x. So if a equals to 3x, it means that a squared must be equal to 3x squared. So we substitute a squared in this equation, equation 3, by 3x squared from equation 2. We do it now, we get that according to equation 3, 9 equals to x squared plus a squared, and a squared according to equation 2 is 3x squared. So in total, according to equation 3, we found out that 9 equals to x squared plus 3x squared. So 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, we can find out that according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So 9 equals to 10x squared. Here we divide this equation 3 by 10, and finally get that according to this equation 3, x squared equals to 9 tenths. Again, going to equation 3, x squared equals to 9/10. Here we take a root out of this equation 3, and finally get that according to this equation 3, x equals to the square root of 9, that is 3, over square root of 10. So if you found out that x equals to 3 over square root of 10 units in its length, according to equation 2, a equals to 3x. So a equals to 3 times x, and x is 3 over square root of 10. So in total a equals to 3 times 3, that is 9 over square root of 10 units in its length. So if you found out that a equals to 9 over square root of 10 units in its length. That is to say, one side, the length of one side of this square ABCD is a, and a equals to 9 over square root of 10 units in its length. So here DC equals to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. And again, according to equation 1, we have already found out that AP equals to 2/3 x. So AP equals to 2/3 x, and x is 3 over square root of 10. So in total AP equals to 2/3 times 3 over square root of 10. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we left only with 2 over square root of 10. So in total we should find out that AP equals to 2 over square root of 10 units in its length. So this is 9/7 AP, that is equal to 2 over square root of 10 units in its length. What is the length of this 9/7 PD? From the drawing, it is very easy to see that PD equals to AD minus AP. PD equals to AD minus AP. Repeat again. PD equals to AD minus AP. So PD equals to AD. AD is A, and A equals to 9 over square root of 10 units in its length. Minus AP. We just like now found out that AP equals to 2 over square root of 10. So in total we found out that PD equals to 9 over square root of 10 minus 2 over square root of 10. That is actually equals to 7 over square root of 10 units in its length. PD equals to 7 over square root of 10 units in its length. So here this is 9/7 PD, is equal to 7 over square root of 10 units in its length. In the next step, we join points P and C together by straight line. By joining points P and C, we can do two right angles. This right angle PDC and this right angle PQC. It is very easy to see from the drawing that the green shape consists of those two right angles. And therefore, the area of the green shape must be equal to the area, to the sum of the areas of the two components that it consists of. That is to say, the area of this green shape must be equal to the area of the right triangle PDC plus the area of this right triangle PQC. So I write it down. So the area of the green shape in total it is equal to the sum of the areas of the two components that it consists of. That is to say, it is equal to the area of this right triangle PDC plus the area of this right triangle PQC. So again, the area of the green shape equals to the area of the right triangle PDC plus the area of the right triangle PQC. What is the area of the right triangle PQC? The area of the right triangle PQC equals to the base PD. Again, what is the area of the right triangle PDC? The area of the right triangle PDC, the area of the right triangle PDC equals to the base PD times the height DC over 2. That's the area of this right triangle PQC. What is the area of the right triangle PQC? The area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. So repeat again, so remember that the area of the right triangle PDC equals to the base of the triangle that is PD times the height that is DC over 2. And the area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. PD equals to 7 over square root of 10 units in its length times DC. DC equals to A and A equals to 9 over square root of 10 units in its length. Divided by 2. So repeat again, the area of the right triangle PDC equals to the base PD that is 7 over square root of 10 times the height that is DC that is 9 over square root of 10 divided by 2. Plus the area of the right triangle PQC that is equal to PQ, the base PQ that is 2 times the height PC that is 3 divided by 2. So the area of the right triangle PQC is 2 times 3 over 2. 2 over 2 is 1, so we left only with 3. What is the value of this expression? We have 7 times 9 is 63 over square root of 10 times square root of 10 is 10 over 2 plus 3. 63 over 10 over 2 is 63 over 10 times 2 plus 3. We have here 63 over times 2, that is 20 plus 3. So here we multiply 3 by 20 and then we divide it by 20 in order to become factor with this number, and you get that in the numerator we have 63 and 3 times 20 is 60 divided by 20 plus 3. 3 multiply 3 by 20, so there's not plus 3. So in total we found out that 63 plus 60 is 123 over 20. 123 over 20 is 6.15 square units. So actually, I found out that the area of this green shape, it is equal to either 123 over 20 square units, so in terms of numbers, the area of this green shape equals to 6.15 square units. We finished with the first question. In the next step, I will present to you the second question, and we solve the second question of this lecture. Our mission in the second question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. Those three angles, they're all right angles. In addition, we know that OB equals to 5 units in its length. That is to say, the radius of this quarter circle AOB is equal to 5. And we also know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. First of all, we join points O and P together by a straight line. And we also join points O and Q together by a straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement here rule 20. So I'll click quickly on rule 20. According to rule 20, in front of equal arcs in the circle, there are equal center angles. So in the drawing we have a circle, and we know that arc AB equals to arc CD in its length. In front of this arc AB we have this center angle alpha, while in front of this arc CD we have this center angle beta. And because of the fact that those two center angles are both located in front of those two equal arcs, they must be also equal to each other. That is to say, center angle alpha equals to center angle beta. So can I implement rule 20 in our drawing? Why? Because in our drawing, arc AP equals to arc PQ equals to arc QB. In front of this arc AP, we have this is center angle AOP. In front of this arc PQ, we have center angle POQ. This center angle POQ. And finally, in front of this arc QB, we have center angle QOB. And because of the fact that those three center angles AOP, POQ, and QOB are located in front of those two equal arcs AP, PQ, and QB, they must be also equal to each other in their sizes. So if we define the size of this center angle AOP as x, then the size of this center angle POQ must be also equal to x. And the size of this center angle QOB must be also equal to x because of the fact that they are equal to each other. So actually, x plus x plus x, that is 3x, equals to the big angle AOB. It is very easy to see that x plus x equals to the big angle A or B. So I write it down. We also found out that 3x equals to angle A or B. From one side, but from the other side, A or B, angle A or B equals to 90 degrees in its size because of the fact that A or B is a quarter circle. So we can write here that angle A or B equals to 90 degrees in its size. And from this equation, 3x equals to angle A or B equals to 90 degrees, we will derive that 3x equals to 90 degrees. So here we divide this equation by 3 and finally get that the missing angle x equals to 90 degrees over 3 is 30 degrees. So this is set angle A or B, that is equal to x, and x equals to 30 degrees in its size. This is set angle P or Q, that is also equal to x, and x equals to 30 degrees in its size. And finally, this is set angle Q or B, that is also equals to x, and x equals to 30 degrees in its size. In the right angle M or P, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees in its size, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right angle N or Q, this angle equals to 90 degrees, this big angle equals to 30 degrees plus 30 degrees, which is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the same rule. OP equals to OQ, they are both the radii of this quarter circle, that is equal to 5, and therefore they are equal to each other. So write it down. OP equals to R, that is the radius of the circle, the radius of the quarter circle, that is 5. OQ is also equals to R, that is the radius of the circle, that is equal to 5. So in the next step, I'll copy this right angle MOP and this right angle NQO in a new page, and we prove that those two right angles can go into each other according to angle side angle rule. Okay, those are the two right triangles. This is the right triangle MOP, and this is the right triangle NQO that I call it from the original drawing. So, why those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees, and therefore they are equal to each other. So, okay, this is again MOP. In the right triangle MOP, and it is equal to this angle, that is actually angle NQO, in the right triangle NQO. They are both equal to 30 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees, and therefore they are equal to each other. So actually, this is angle MPO in the right triangle, triangle MOP, and it is equal to this angle, which is actually angle NOQ. In triangle NQO, they are both equal to 60 degrees, and therefore they are equal to each other. And finally, side PO in the right triangle MOP equals to side QO in the right triangle NQO. They are both the area of the circle that is equal to 1, and therefore they are equal to each other. So let it know OP equals to OQ equals to the radius of the circle is equal to 5. So we actually proved that those two angles and the side that is included between those two angles, that is side OP, the right triangle NQO. Again, those two angles and the side that is included between those two angles, that is side OQ of the right triangle NQO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is actually again OP, and this right triangle MOP. And therefore, we actually prove that those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the right triangle MOP is congruent this is congruent to the right triangle NOQ according to side angle rule. And from the fact that those two right triangles congruent to each other, we will derive that they have also the same areas. Why? Because any two right triangles that congruent to each other must also have the same areas. That is to say, the area of this right triangle MOP equals to the area of this right triangle NQO. So I write it down. The area of the right triangle MOP equal to the area of the right triangle NQO. Okay, again, if we found out that the area of the right triangle MOP is equal to the area of the right triangle NQO. From the drawing, first of all, we will define this point as point S. from the drawing it is very easy to see that the right triangle MPO consists of this green quadrangle MNSP and this right triangle NSO. And therefore, the area of this right triangle MPO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the green quadrangle MNSP, this green quadrangle, plus this right triangle NOS. So I write it down. The area of the right triangle MOP must be equal to the area of this green quadrangle MNSP plus the area of this right small triangle NSO. So I repeat again, the area of the right triangle MOP must be equal to the sum of the components or to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of quadrangle MNSP plus the area of the right triangle NSO. And according to the equation 1, the area of triangle MOP equals to the area of the right triangle NQO. This is the right triangle NQO. It is very easy to see that the right big triangle NQO consists of two small triangles. It consists of this small right triangle NSO, and it also consists of this triangle OSQ. And therefore, the area of this right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this triangle SOQ. So I write it down. The area of the right triangle NQO in total must be equal to the area of the right triangle NSO plus the area of this triangle OSQ. I repeat again, the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of triangle OSQ, because it consists of two components. So, in this is equation 1. In this equation 1, we have the area of the right triangle NSO on both sides of the equation. So we subtract the area of the right triangle NSO from this equation, equation 1. So actually, the area of triangle NSO will get cancelled, and you're left only with the area of quadrangle MNSP that is equal to the area of triangle OSQ. So actually found out that the area of this green quadrangle MNSP is equal to the area of this triangle SOQ. Our mission is to find out the area of this green shape. So, what is the area of the green shape? Actually, from the drawing it is very easy to see that the area of this green shape equals to the area of quadrangle MNSP plus the area of this green small shape PSQ. So I write it down. the area of this green shape is equal to the area of quadrilateral MNSP plus the area of this green shape PSQ. So if it again, I can find out that the area of the green shape in total is equal to the area of quadrilateral MNSP plus the area of the green small shape PSQ. But we already found out that the area of quadrilateral MNSP is equal to the area of triangle OSQ. So we can substitute the area of quadrilateral MNSP by the area of triangle OSQ because they are equal to each other. We do it now and you get that in total the area of the green shape is equal to again the area of quadrilateral MNSP. It is actually the area of triangle OSQ. So substitute the area of quadrilateral MNSP by the area of triangle OSQ plus the area of shape PSQ. So actually I found out that the area of the green shape equals to the area of triangle OSQ plus the area of this small shape PSQ. But the area of the small shape PSQ plus the area of triangle OSQ, it is exactly equal to the area of sector POQ. Okay. Again, the area of triangle OSQ plus the area of the green shape PSQ is equal to the area of sector POQ. Here the rounded line above POQ is the sign for a sector. It means the sector POQ, and the square brackets is the sign for the area. So in total this sign means the area of sector POQ. So what is the area of sector? So actually found out that the area of the green shape equals to the area of sector POQ. So what is the area of sector POQ? Actually, the area of sector POQ equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. So repeat again, the area of the sector POQ is equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. The radius of this quarter circle is 5, so r squared is 5 squared, that is 25, so pi r squared is 25 pi, and 30 degrees over 360 degrees is 1 over 12. 25 pi over 12 is 6.545 square units. So actually found out that the area that we are looking for in this question, that is the area of this green shape, is equal to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape is equal to 6.545 square units. So we finish with the second question. In the next step, I'll summarize the ratio. We start with the first question, of course. Our mission in the first question is to find out the area of this great shape. So, in the drawing we have square ABCD. This is angle PQC, that is the right angle. This is line segment PQ, that is equal to 2 units in its length. This is line segment QC, that is equal to 4 units in its length. Again, our mission is to find out the area of this great shape. First of all, we know that all those 4 angles inside square ABCD are right angles, and we also know that all the 4 sides of square ABCD are equal to each other. So we define one side of this square ABCD as say, therefore AD equals to DC equals to CB equals to BA equals to A. Then we define this line segment PQ as X. Therefore, let me say line segment AQ must be equal to AB, that is A, minus QB, that is X. So in total AQ equals to A minus X units in its length. In the next step, we define this angle QCB as alpha. So in the right triangle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. That is to say, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, therefore it is absolutely straight line. So if you focus on this side of the square of the straight line AB, or if you focus on the right side of the straight line AB, here at point Q. So here the sum of the angles must be equal to 180 degrees, according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of A? Which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, this angle that is 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So this missing angle must be equal to alpha according to rule 3. In the right triangle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copy this right triangle AQP in this right triangle QBC in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. Okay, those are the two right triangles that are coming from the original drawing. This is the right triangle APQ, and this is the right triangle QBC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the three angles in this right triangle AQP are correspondingly equal to all those three angles in the right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP in the right triangle APQ, or side QB in the right triangle QBC is equal to side AQ in the right triangle APQ, or side BC in this right triangle QBC. And it is also equals to PQ, side PQ, in this right triangle APQ, over side QC, in this right triangle QCB. Again, if we follow this according to equation 1, AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. QB is X, AQ is minus X, BC is A, PQ is 2 and QC is 3. So in total, according to equation 1, we can find out that AP over X equals to A minus X over A, and it is equal to 2/3. those two expressions are equal to each other, therefore we created equation 1 from those two expressions that are equal to each other. That is to say, according to equation 1, AP over x equals to 2/3. Here we multiply this equation, equation 1 by x, and found out that according to this equation 1, AP equals to 2/3 x. So actually, those two expressions are also equal to each other, therefore we created equation 2 from those two expressions that are equal to each other. So according to equation 2, actually a minus x over a equals to 2/3. Here of course multiply this equation 2, and find out that according to this equation 2, 3 times a minus x equals to 2a. We open the brackets on this side of this equation 2, and find out that 3a minus 3x equals to 2a. Here we subtract 2a for this equation 1, and find out that 3a minus 2a equals to a, so a minus 3x equals to 0. Here we added 3x to this equation 1, and find out that a equals to 3x. In the next step, I copied this right QBC in a new page, and we implemented the Pythagoras theorem on this right QBC. According to the Pythagoras theorem, in an right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle QBC, that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. Again, according to the Pythagoras theorem, in this right triangle QBC, QC squared equals to QB squared plus BC squared. The hypotenuse QC is 3, therefore QC squared is 3 squared, that is 9, and it is equals to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is a, therefore BC squared is a squared. So in total, according to equation 3, we found out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation 3 by 3x squared for this equation 2. We did it, and we found out that 9 equals to x squared plus a squared. A squared is 3x squared according to equation 2. So in total, we found out that according to equation 3, 9 equals to x squared plus 3x squared. So 9 equals to x squared, and 3x squared is 9x squared. So in total, we found out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared, so 9 equals to 10x squared according to equation 3. We divided this equation 3 by 10, and we found out that x squared equals to 9 tenths. So here we look out of this equation 3, and find out that x equals to the square root of 9, that is 3, over the square root of 10. According to equation 2, a equals to 3x, so a equals to 3, and x is 3 over the square root of 10. So in total, a equals to 3 times 3, that is 9, over the square root of 10 units in its length. Again, a equals to 9 over the square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. So AP equals to 2/3, and x is 3 over the square root of 10. We have 3 in the numerator and 3 in the denominator, so 3 can get cancelled. And we're left only with 2 over the square root of 10 units in its length. So in total, if we found out that AP, this is 9/7 AP, that equals to 2 over the square root of 10 units in its length. What is the length of this 9/7 PD? PD equals to AD minus AP. Again, PD equals to AD minus AP. So repeat again, PD equals to AD minus AP. AD equals to A, so AD equals to A, and A equals to 9 over the square root of 10. So in total, PD equals to 9 over the square root of 10. Again, AD equals to 9 over the square root of 10. minus AP. AP is 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10 units in itself. So in total, if we found out that this answer PD equals to 7 over square root of 10 units in itself. In the next step, we join points P and C together by a straight line. By joining points P and C, we can do two right angles. This right angle, this is right angle PDC, and this is right angle get PQC. For the moment, it is very easy to see that the green shape consists of those two right angles. Consists exactly those two right angles, and therefore the area of the green shape must be equal to the sum of the areas of the two components that it consists of. That is to say, the area of this green shape must be equal to the area of this right angle PDC plus the area of this right angle QPC. So if we found out that in total, the area of the green shape equals to the area of triangle PDC plus the area of triangle PQC. The area of triangle PDC, the right angle PDC is the base that is PD times the height that is DC over 2. The area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. And again, the area of the right triangle PDC is the base PD times the height that is DC over 2, and the area of the right triangle PQC is the base PQ times the height QC over 2. PD is 7 over square root of 10, DC is 9 over square root of 10 divided by 2. PQ is 2, QC is 3 divided by 2. So, what is the value of this expression? We have 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2. Here we have 2 in the numerator and 2 in the denominator, so 2 we can cancel, and then have only 3. We have 63 over 10 over 2 is 63 over 10 times 2 plus 3. And 63 over 10 times 2 is 63 over 20. Plus 10 times 2 is 20 plus 3. Here we multiplied 20 by 3 and then we divided by 3 in order to overcome out of this number. And finally found out that in the numerator we have 63 and 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. 123 over 20 is 6.15 square meters. So in total we found out that the area of this green shape equals to either 123 over 20 square meters, so in terms of numbers, the area of this green shape equals to 6.15 square meters. So we finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. Our mission in the second question is to find out the area of this green shape. So in the moment we have quarter circle AOB. OB equals to 5, that is to say the radius of this quarter circle equals to 5 units in its length. All those three angles are right angles. In addition, we know that arc AP equals to arc PQ equals to arc QB. In the first step, we join points O and P together. We join points O and P together by a straight line, and we also join points O and Q together by a straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement here rule 20. So I put rule 20, according to rule 20, in front of equal arcs in the circle, there are equal central angles. So in the moment we have a circle, and we know that this is arc AB, that is equal to arc CD in its length. In front of this arc AB, we have this perpendicular angle alpha, while in front of this arc CD, we have this certain angle beta. And because of the fact that those two certain angles alpha and beta are located in front of those two equal arcs, they must be also equal to each other. That is to say, certain angle alpha equals to certain angle beta. So we can actually implement rule 20 in our drawing. Why? Because in our moment we have RKP that is equal to our PQ and it is equal also to our QB. In front of this RKP we have this center angle AOP. In front of this RPQ we have this center angle POQ. And finally in front of this RQB we have this center angle QOB. And because of the fact that those three center angles AOP, POQ and QOB, they are all located in front of those three equal arcs, they must be also equal to each other in their sizes. That is to say, the size of this center angle AOP must be equal to the size of this center angle POQ, and it also must be equal to the size of this center angle QOC. So if you define the size of this center angle AOP as x, then triangle POQ must be also equal to x, and center angle POQ must be also equal to x, and center angle QOB must be also equal to x, because they are equal to each other according to Rule 20. So if you found out that x plus x plus x, that is 3x in total equals to angle AOB. It is very easy to see that angle AOB equals to x plus x plus x. So from one side, angle AOB equals to 3x. From the other side, angle AOB is a right angle. Why angle AOB is a right angle? Because of the fact that AOB is a quarter circle. And from this equation, 3x equals to angle AOB equals to 90 degrees. We will derive that 3x equals to 90 degrees. We divided this equation by 3 and found out that the missing angle x equals to 30 degrees in its size. So, center angle AOP equals to 30 degrees in its size, center angle POQ equals to 30 degrees in its size, and finally center angle QOB also equals to 30 degrees in its size. So in the right angle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees in size. According to the rule, it said that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in this right angle NOQ, the right angle NOQ, this angle equals to 90 degrees. This angle equals to 90 degrees. This angle equals to 30 degrees plus 30 degrees is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the sum rule. OP equals to OQ. Both those two line segments are the radii of the circle is equals to 5, and therefore they are equal to each other. So in the next step, we'll cover this right angle MOP and this right angle POQ. In the new pages, we prove that those two right angles can go into each other according to angle side angle rule. So those are the two right angles. This is right angle MOP, this is right angle NQO that are going from the original drawing. So why those two right angles can go into each other? First of all, those two angles are both equal to 60 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, and therefore they are equal to each other. And finally, OP equals to OQ equals to 5. Above the radii of the circle is equal to 5, and therefore they are equal to each other. So I should prove that those two angles and the side included between those two angles, that is side PO and the right angle MOP, are correspondingly equal to those two angles, and the side included between those two angles in the right angle NOQ. And the side is included between those two angles, that is side OQ and the right angle NQO. Therefore, we can prove that those two right angles can go into each other according to angle side angle rule. And for the fact that those two right angles can go into each other, we derive that they have also the same areas. Why? Because any two triangles that can go to each other must also have the same areas. So if you found out that there are this right angle MOP is equal to the area of this right angle NQO. Again, according to equation 1, the area of triangle MOP equals to the area of triangle NQO. But because of the fact that this is triangle MPO, it consists of this ring quadrilateral MNSP, and it also consists of this right triangle NOS. And therefore, the area of this right triangle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this ring quadrilateral MNSP plus the area of this right triangle NOS. So Repeat again. If you found out that the area of triangle MOP equals to the sum of the areas of the two components that it consists of. That is to say, is equal to the area of quadrangle MNSP plus the area of triangle NSO. And you know the triangle MOP equals the area of triangle MOP equals to the area of triangle NQO. This is the right triangle NOQ or NQO. It is very easy to see that this big triangle NQO consists of two small triangles. It consists of this small triangle NSO, and it also consists of this triangle SOQ. And therefore the area of the big triangle NOQ must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right small triangle NSO plus the area of this triangle SOQ. So again, we found out that the area of triangle NQO is equal to the sum of the areas of the two components that it consists of. That is to say, it is equal to the area of the small right triangle NSO plus the area of triangle SOQ. We have the area of triangle NSO both sides of the equation, so we can subtract the area of triangle NSO from this equation. So after we subtract the area of triangle NSO from this equation, so the area of triangle NSO get cancelled. We left only with the area of quadrangle MNSP that is equal to the area of triangle OSQ. So if you found out the area of this great quadrangle MPSN is equal to the area of this right triangle OSQ. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the domain it is very easy to see. The area of this green shape equals to the area of quadrangle MPSN plus the area of this small shape PQS. Okay, again, from the domain it is very easy to see that the area of the green shape in total equals to the area of quadrangle MNSP plus the area of the small shape PSQ. But we already found out that the area of quadrangle MNSP equals to the area of triangle OSQ, therefore we can substitute the area of the quadrangle MNSP by the area of triangle OSQ. We need it. We actually found out that the area of the green shape in total equals to the area of quadrangle MNSP is equal to the area of triangle OSQ, therefore we substitute the area of quadrangle MNSP by the area of triangle OSQ plus the area of the small shape PSQ. So in total we should found out that the area of this green shape equals to the area of this triangle QOS plus the area of this green shape PSQ. But the sum of the areas of those two components is equal to the area of sector POQ. It is very easy to see that the sum of the areas of those two components is equals exactly to the area of sector POQ. And the area of triangle OSQ plus the area of the green small shape PSQ, it is equal exactly to the area of sector POQ. But so in total we should found out that the area of the green shape equals to the area of sector POQ. But what is the area of this sector POQ? Actually the area of sector POQ equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. So I repeat again, the area of sector POQ equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees over 360 degrees. The radius of this quarter circle r equals to 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi, and 360 degrees over 30 degrees over 360 degrees is 1 over 12. So in total we should found out that the area of the green shape equals to either 25 pi over 12 square meters, or in terms of numbers, the area of the green shape equals to 6.545 square meters. So again, the area of this green shape is equal to either 25 pi over 12 square meters, so in terms of numbers, the area of this green shape is equal to 6.545 square meters. Okay, thank you very much.